Okay children, welcome back to the online tutor. So today I'm going to conduct the probability third tutorial, right? So previous tutorial we have discussed about the conditional probability and also the independent events, right? So now today I'm going to discuss the very important two theorems, right, in this tutorial, which is total probability theorem and the Bayes theorem. Right? Before that I'm going to discuss one more important two questions, right? So these two questions are really important to write to answer the 2012 LL paper, right? 2015 LL paper, right? So these LL papers are based on that knowledge, right? So you can see in the board A intersection B intersection C, which is equal to PA into PB over A into PZ over A intersection B, right? So this is actually the happening of A, right? So what is this? This is the conditional probability that happening B when the A is occurred, right? So this is the conditional probability that the event C happening, right? When the A and B are happen, right? So this is the conditional probability, right? So I'm going to prove this, right? I'm going to prove this using the right hand side. The right hand side we had PA PB over A C over A intersection B, right? This is PA, no? So this is P B intersection A over PA. So what is this? This is PA intersection B intersection C over PA intersection B, right? So this is under the conditional probability definition, right? So now you can see this is getting cancelled, right? So therefore it's coming A intersection B intersection C are left hand side, LHS, left hand side. So this is the way of proving these kind of situations, right? So actually this is the probability that the both three events are happen, right? So first A happen, after the B happen, after the C happen, right? Let's move to the example, right? So you can see now a ball contain a bag contain 9 blue balls, 7 white balls and 4 green balls. If their balls are taken from this bag at random, find the probability that all 3 balls will be blue, 2 balls will be white and one will be blue. At least 1 ball will be white. The 3 balls will be 3 different colors, right? Okay, so now I am going to draw the bag. This is the bag, right? Blue 9 balls, white 7 balls, green 4 balls. If 3 balls are taken from this bag at random, find the probability that all 3 balls will be blue, right? Actually, to solve this question, we have 2 ways, right? The first way is drawing decision tree, right? Another one is using the conditional probability, right? So now I'm going to use the conditional probability knowledge, right? So how to do this? So first of all I'm going to define the events. This is outside ball is blue, white, gray. PB, PW, PG, right? B mean we have 9 B balls now, blue balls now, and it's 16 plus 4, it's 20, 9 over 20. White ball, which is 7. Green ball, 4. Right, so this is the probability of the selecting blue ball, selecting white ball and selecting green ball, right? So likewise, so the first question, so the part A, all 3 balls will be blue, right? So first of all I'm going to define another variable which is I is 1 2 3, right? The selected time, right? The first selected ball, second selected ball, third selected ball, right? I equal 1 2 3. The first question, all 3 balls will be blue. So that means the first ball is blue, intersection. Second ball is blue, intersection. Third ball is blue. So likewise. These three balls are taken randomly, one at a time, right? So the first one B1, B2 and B3, right? All balls are black balls, right? So how to find these, right? So first of all, I'm going to take the first ball, right? It's B1. And next B2 when B1 was happened. And after that B3 after B1 and B2 happened. Alright, so this is like the previous one. And what is the probability that the first ball is blue? It's 9 over 20. And the probability of the second ball is blue, right? When the first ball is blue. So it's the one is now outside. So right. So I'm just thinking the balls are taken without replacement, right? It's 8 over 19. So the next one, again the third ball, it's again blue, and 7 over 18. So it's cancelled. 4, 5. So 7 over 95. This is the probability that the all three balls are blue, right? Okay, let's move to the second one, right? All two balls will be white and one will be blue, right? All two balls will be white and one will be blue. So two balls will be white means the first one is white, second one is white, and the third one will be blue, right? Actually this can be happen with this way, blue first after the white, right? And first white, blue and white. So it can be happening that all way, right? So therefore, so you can see here these two balls, blue balls are same, and we have all together three balls. Therefore factorial 3 divided by the same thing happening is 2, right? So we have discussed these things in our permutation and combination lessons, right? So the balls are selected, right? The balls are selected at a time, right? And two balls are same and one ball is two balls are white and the other ball is blue, right? Then so all together it's three balls, right? And the same, we have same two balls, it's white, and we divide by the factorial 2. So this is actually the permutation, the second theorem, right? So happening of the first white ball, PW1 and W2 when the W1 happened, B3 after the white 1 and white 2 happened, right? So the probability of the being white ball, it's 7 over 20, and the white again 6 over 90, and again blue is 18, but all are 4, right? So now it's cancelled. 5, 3, 15 into 19, right? So this is the answer of the part B, right? The probability of selecting. I'm sorry, I forget that root factorial 3 to 1, again 2 1, right? It's into 3. 5, 7 over 95. 7 over 95, the answer of the part B. And the next one, at least one ball will be white. At least one ball will be white. So how to do this? At least one ball will be white mean we can think it like the selected ball is white and the other balls will be green or blue, right? And the and we can think it like selected two balls is white and the other one is not white, right? and the other another way, selecting all three balls are white and the all three balls are white, right? So therefore these three situations should be added. Selecting the first selection is white and the others are not. First selection no, otherwise second selection no, third. Anyway, there's a one ball which is white is selected and two balls will be white and the three balls, all three balls will be white. So these three situations should be added. But now at least one ball, right? What do you think about a non-white ball? Like the selected ball is not a white. The one is not a white. The second one is not a white. Third one is not a white. Right? So these three situations, right? These three, the balls are not white. Not white. This is a green or blue. Right? Therefore, if you find the probability of the selecting ball is not a white, right? So you can subtract 1 minus this thing, W1 dash, W2 dash, W3 dash, right? So this answer gives at least one ball will be white, right? The total probability is 1, so I am subtracted, not selecting any white ball, right? So therefore you will get at least one ball will be white. So this is PW1 into PW2 dash over W1, PW3 dash, W1 and W2 dash are. So non-white mean, so all we have 7 white balls in non-white mean 20 over 13 over 20. 9 white, it's 12 over 19, 11 over 18, so likewise. Thirteen into 11, 30 over 19. This is the probability of all three balls are non-white. So it's 13 1 4 3 0 2 517, right? But we need to find at least one ball will be white, no? At least one ball will be white mean. At least one ball will be white. At least one will be white. So I'm going to subtract this probability by 1, right? So the total sample space is 1. The probability of occurring of the total is 1. 143 570 570 143 570 7 right 6 mean 2 570. So this is the probability of at least one ball will be white. So it can be only one can be white, only two can be white, only all three can be white. So all line here. That is what they ask in this fourth part. Okay, let's move to the next sum. So the next part of this question. The three balls will be of three different colors. Three different colors. Three different colors mean the first selection will be white, blue, as you, and the second selection is white, and the third one should be not white, it's green. Okay, the first one blue, white and green likewise. So actually, so these three can be happen with white, blue, green, and the green, white, blue, right? Likewise, we have factorial 3 separate ways of occurring that situation, right? So factorial 3 means 3 into 2 is 6, right? Actually, we can write the 6th way of happening this blue, white, green, right? With a different way. So then, the B1 is happening is 9 over 20 now. Again the white is happening 7 over 19 now, because one ball is outside now. And the next one is 2 balls are outside, then 18, the green is 4. 5, 2. 7 over 190. 5 into 2 now 10. It's 190. 7 over 190. So this is the probability of all balls will be different colors, right? The 3 colors, right? Okay, children, let's move to the next sum. A box contains 7 red balls, 4 white balls, 9 black balls. If 3 balls are taken at random from the box, find the probability of all 3 balls will be red. So, okay, this is again it's like a previous one. With 7 are red balls. Sevens are red ball. 4 are white ball. 9 are black ball. Right, so this is a red ball or white ball. Outside ball is white. Outside ball is blue. Black, sorry. So PR it's again 27 all 3 balls will be red. So I equal 1, 2, 3 likewise, right? All 3 balls will be red. R1 intersection R2 intersection R3. Right, so PR1, PR2 over R1, PR3 over R1 intersection R2. So PR1 means 20 over 7. R2 means, right, again it's 6 over 19. 5 over 18. 35 over 60 into 90. So this is the answer of the first one. The next one, all 3 balls will be white. All 3 balls will be white. So that means W1 white, W2 white, W3 white. So PW1, W2 over W1, W3 over W1, W2. So all 3 balls will be white mean. The first one is white, it's 20 and 390, 280, 6, 3, 15 into 90 over 1. Okay, this is the second part. Part B, right? And what about part 3? 2 will be white and 1 will be red. 2 will be white and the 1 will be red. R3. PW1, W2 over W1, R3, W1, W2. W1 means 20 over 4 over 20. Again 3 over 19. And the red is, we have 7 but out of 80. It's 5, 6, 7 over 30 over 90. But actually this can be changed, right? These can be changed, right? So factorial 3 divide by factorial. See, because we are not considering the order, so it can be any order. W1, W1, right? R2 and W3. So likewise, we have 3 factorial divide by, we have 2 same factorial 2, right? It's multiplied by 3, it's 10, 7 over 190. This is the part B. And what about part C? Part C, 2 will be white and, part D, 2, at least 1 will be white. At least 1 will be white mean, again the same thing, white dash, dash, white dash. PW1 dash into PW2 dash over W1 dash, PW3 dash over 1 dash, 2 dash. So this is white dash mean. So all together here, we have white balls 4, right? Then it's 16 over 20. Except white, no? And except white, 19 over 50, 19 over 18 over 40. So except white, right? So we can simplify it like 3, 4, 4. This is the answer of non-white, right? So we need at least 1 white, no? At least 1 white. It's 1 minus 28 over 57. Then it's 9, 57, 19, right? It's not 19, it's 29, right? Okay, one more. 3 balls will be 3 different colors. 3 balls will be 3 different colors. So which means R1, Y2, right? So R1, Y2, when the R1 is occurred, B3, with the R1 and W2 both are occurred. So R1 means 7 over 20, white mean 19 over 4 over 19, 80. Seven over 109. But you should understand here this can be interchanged, right? The factorial 3 means 3, 2, 1, factorial 3. 42 over 190. Actual children, so the previous sum can be done using the tree diagram, right? It's the tree diagram. So how to do that? So you have to draw the tree diagrams. So we have three kind of balls now, right? So three kind of mean red, white and black. So selecting first ball is red, it's 20 over 7. White is 4 over 20 and the 9 over 20. So likewise, selecting second ball red means again 3, right? It's 6 over 20. Sorry, 19, right? 4 over 19, this not change, 9 over 19, right? If you added this 6, 9, 9, 4, right, it will be 19, right? So the white means, the first one was white and the here red, white, black, red, white, black. Okay, then first one is white mean white should be subtracted 3. And here red is 7, it's not change, 19, 90. So likewise, right? So this is first selection, second selection and third selection. So third selection means you have to draw it again, right? So actually it's difficult to draw in tree diagram for the three situations, right? So it's very large and calculation is really difficult. So that is why we are using conditional probability to represent our any answer, right? So actually if it is, so if they ask to find the fourth one will be red, so it's very difficult to draw it now. It's very difficult to continue the diagram. But if you're using the conditional probability, you just need to only put the condition way, right? So first one is right, second one is right, third one red, fourth one red. So likewise, whatever the chance, right? Whatever the chance, so you just need to continue with the conditional probability scenario, right? Then the answer will be getting easiest way. So that is why we are using conditional probability instead of using the decision tree, right? Okay children, the next one is total probability law. Total probability law means the definition: if A1, A2, A3 ... AN are mutually exclusive and exhaustive events where A1 greater than 0 for all I equal 1, 2 ... n, and if B is any random event. So we can draw it like this is my total sample space, right? Omega. And A1, A2, A3 ... AN are mutually exclusive and exhaustive n number of events. 1, 2, 3, 4, likewise up to n. 1, 2, 3, 4, likewise up to n, right? Then all are mutually exclusive and exhaustive. So there is another B, random event B. So this is A1, A2, A3, A4, AN. So this is B event. Omega is the total sample space, right? Then they happen in B, right? So this part is right. So likewise, they have n number of partitions here. Okay. So this is total probability theorem. So actually the total probability theorem is focus to find that B, to determine that B. Actually, how B become? B mean B came from A1 union, B coming from A2. B coming from A3. So likewise B coming from AA. Okay. This is the B. B event. B is coming from small partitions from A1 to AN. So this B, right? So these all are mutually exclusive and exhaustive. No? So we can write it like the probability of this whole thing. The probability of this whole thing. But these are union. The union and the all partitions are not intersected to each other. Therefore, you can write it like A1 plus B A2 dot B AA. Right? The reason mutually exclusive and exhaustive. So that is why which are not which doesn't have any intersections. Right? Those are all are added. So what is this? So this is actually A1 B over A1. This is PB B over A2. Likewise PB, this is A2, right? A2 dot AN B over A. So likewise all are added. Therefore you can write your answer like PB equal sigma I goes to 1 to N P, this A1 A2 dot AN AI. This is B over A1 B over A2, likewise B over AN. This is the total probability of the event B. So the complete probability of happening the event B actually. So you just need to memorize that formula. This is very important part in our probability lesson. And also the proof should be memorized, right? Sometimes in the exam the proofs are asked. Okay, let's move to example. 50 of the production of the factory is produced by machine A1, 30% by machine A2, and the rest by machine A3. 10% of the good product produced by machine A1, 8% of the goods produced by machine A2, and 55% of the goods produced by A3 are defective. So defective is important part, right? These machines generated, right, the defective products. When the piece of goods from this production is chosen at random, what is the probability that it will be defective? So first of all, I am going to define my variables. So A1 means machine A1 production, A2 production, A3 production. PA1 is 50%, PA2 is 30%, PA3 the rest is 20%. Okay, and I'm explaining another variable. I'm defining another variable, the defective product. defective product. Right? So the defective product can be designed, right? 10% of good produced by A1 is defective. So A1 machine generated defective products, which is 10%. A2 machine generated the defective product is 8%. A3 machine generated 5% out of 100, right? So we need to calculate when a piece of good from this production is chosen at random, what is the probability that it will be defective? So we need the total probability now. So what is the equation of the total probability, right? So it was PB equal sigma I goes to 1 to n PAI B over A. So PAI means the first one, this one into that one. 50 into 100, 10 over 100. 30 into 8, 100 into 100. Plus 20 into 5, 100 into 100. So likewise, actually some zeros are cancelled. 50 plus 24 plus 10,000, right? So 60 and 84 out of 1000, then 8.4 out of 100, 84%, 8.4, right? 8.4 percentage produced, right? By these all machines, right? The products are defective. So that is the probability of defective product, right? P defective. So it can become from A1, A2, A3, all, right? Okay, let's move to another sum. A man can travel from work by either train or bus. One certain day, the probability of the traveling to work by train is 1 over 4. The probability of his traveling to work by bus is 3 over 4. The probabilities of his being late for work by these two modes of transports are 1 over 5 and 1 over 8 respectively. What is the probability that he comes late for work on a particular day? Right, so I'm going to first introduce my variables. So I'm taking A1, A2. A man travels to work by train. A man travels to work by bus. And B, he comes late. So what is PA1, PA2, PA3? So PA1 means traveling to work by train. It's 1 over 4, 3 over 4. Sorry, no A3s. He comes late when he travels on train. He comes late when he travels by bus. B over A1. One over 5. 1 over 8. What is the probability that he comes late for work on a particular day? So it can become A1 PB over A1. I'm just writing the total probability here. PA2 B over A2. So now we can substitute the values. This is 1 over 4 into 1 over 5 plus 3 over 4 1 over 8. So the PB will be 1 over 20 plus 32 3. Then 32 plus 20 over 32. So this is the probability of he getting late. He comes late, right? Either traveling on a bus or the train. Okay, let's move to the next sum. A restaurant has 3 bakeries, A, B, C. 50% of the breads from his restaurant are produced at the bakery A, 30% of the bakery B, 20% of bakery C. 8 of bread produced at bakery A are found to be only half baked. 10% of bread baked at B is 15% of bread baked, and at the bakery C are found half baked. When a loaf of bread is randomly chosen from the total production of the bread baked in a day, and this chosen loaf is half baked, right? A, B, C. So I assume A1, A2, A3, right? This is A bakery production, bread production, right? B bakery bread production, C bakery bread production. So PA1, PA2, PA3 are separately 50% out of 100, 30%, 20%. So another variable is design, half baked loaf of bread. So probability of half baked which found from A1, BA2, BA3. Eight product is out of 100 A, 10 out of 100, 15 out of 100. Okay, so these are the data of the bakery production, right? So we need the total probability of a selected loaf of bread is half baked. So we need PB now again. So PB, right? So PB means sigma I goes to 1 to n, PAI, B over AI. So AI means 50% out of 100, 8 out of 100, plus 30%, 100, 10 over 100, 20%, 100 over 100. So 1 0 is cancelled. 40,000, 30,000, 30,000. Four, 7, 10. So which means 10% of breads are half baked, right? So that is what we need. So it can be coming from the A bakery, B bakery, C, all total, right? The total probability we are targeting. So that is what they ask. Okay, I think now you have a brief idea about the total probability theorem, right? So the total probability theorem means you just need to define the all variables, right? And A1, A2, A3 and B, and just connect all with the individual way, then you will get the final B. So B can be a half baked loaf, right? B can be a with an accident case like the previous one, and the defective one, then all, right? So the only thing is you just need to understand the scenario and define the variables and find the total probability theorem. So now I'm going to discuss this example using Venn diagram, right? Sorry, not Venn diagram, decision tree, using decision tree, right? Okay, so I'm drawing the decision tree, right? Okay, the first thing is you just need to add all productions, right? This is A1 production, A2 production, A3, and the other one is which is half baked or not, half baked or not, half baked or not, right? So now you can insert the data they have given. So the data was, the first A1 is 50%, no? 50% out of 100. 30% out of 100. 10% out of 100. A1 goods, 8% are defective. And others are not defective. 92 out of 100. So A2 10% are half baked, 90 are not half. The last one 15% half baked, 85 not half baked, right? So you just need to find this and that and just add all. You will get the total probability of the half baked is, which half baked is found, right? Half baked bread was found. That is the connection between the total probability and the total probability main equation and the decision tree. Okay, this is the end of the probability tutorial, right? So the next tutorial I will explain the Bayes theorem, right? The total probability and Bayes theorem are both interconnected, right? So the next tutorial, let's discuss the total probability theorem. And also I put some homeworks to be done, right? So you can try it as a homework. These are under the today sessions, right? And okay, thank you very much for being with us and have a nice day.